Hey everyone, welcome to this explainer. So let me ask you this. Have you ever felt that absolute soul-crushing frustration of writing an amazing feature only to have it sit in a testing queue for weeks? If so, you are definitely in the right place. Today, we're talking about completely transforming your development lifecycle. We're going to look at how to finally move away from those slow manual testing bottlenecks and upgrade to lightning-fast, automated, containerized testing using Docker. Seriously, it's an absolute game changer for shipping high-quality code fast.
All right, here's a quick roadmap of what we're covering today. We'll kick things off with the manual testing bottleneck, look at why we should test in containers, break down the types of containerized tests, build a sample component, execute those tests, and finish up with best practices and debugging. Let's just jump right in.
Section 1. The manual testing bottleneck.
Look, pretty much every software developer out there faces the pressure to ship new code quickly, right? But traditional manual testing, it creates this massive roadblock. You literally have teams of manual testers blocking user acceptance testing or UAT environments for weeks just to run hundreds of regression cases. And during that time, absolutely zero new code can be deployed there. So what happens? You end up batching together all this new code, which, as we know, massively increases your deployment risk. It's a huge bottleneck. The only truly scalable fix here is automated continuous testing. It shrinks that feedback loop from weeks down to literally minutes, letting you ship in small, fast batches. And to pull that off, your regression testing has to be 100% automated.
Moving on to Section 2. Why test in containers?
So, if automated testing is our ultimate goal, how do we make sure those tests actually run reliably everywhere? Well, the magic word here is isolation. Docker completely obliterates that classic developer excuse of, well, it works on my machine, by packaging the entire environment, the dependencies, the libraries, the configurations, into one self-contained unit. You get total consistency across your development pipelines. It's super portable, it scales effortlessly for parallel execution, and the best part? You no longer have to waste hours manually setting up host dependencies just to run a simple test suite.
Which brings us to Section 3. Types of containerized tests.
Before we even touch a line of code, we need a game plan. Testing happens in distinct layers. First up, we've got unit tests. Think of this as your granular, lightning-fast first line of defense. The main goal here is to validate tiny, isolated chunks of your code. They rely on absolutely zero external resources. None. That makes them incredibly fast to run, typically executing automatically every single time you commit code in your continuous integration process. Next up the ladder, we have integration tests. Now, these are inherently trickier than unit tests because we're looking at how various parts of a system actually interact. We might be connecting to external databases or APIs just to ensure that the different software components actually play nice and function together as a whole.
And finally, we reach acceptance tests, or specifically for our Docker setup today, black box tests. This is it, the final quality gate. Here, we treat the application like a completely closed system, a true black box. We test it strictly from the end user's viewpoint to guarantee it actually satisfies the business requirements. A bit later in this explainer, we're actually going to demonstrate spinning this up in a dedicated container that is totally separate from the application itself.
Now check this out. This visual perfectly anchors how we write these tests, the AAA methodology, Arrange-Act-Assert. I mean, some people call it given, when, then, but the logic is exactly the same. You set up your data, you perform the action, and then you verify the outcome. Structuring your code this way is absolutely crucial. It keeps your test suites incredibly clean, super readable, and really easy to maintain.
All right, Section 4. Let's build a sample component.
Okay, enough theory. Let's get into a practical application. We're going to rapidly spin up a Java Spring Boot component to manage animal species and their races. We kick things off by bootstrapping a Java project with Spring Initializer. Then, we define our data models in repositories, create some REST controllers to handle our HTTP requests, and finally, wire the whole shebang up to an H2 in-memory database. Now, what's really cool about using H2 here is that it completely wipes our data upon each restart, so we literally get a perfectly clean slate every single time the container runs.
Here's what that logic looks like in action. The Spring Boot controller maps standard endpoints like /races straight to our backend logic. And to support that, our database properties configure the H2 setup, enabling that in-memory database with no password required. It's just a beautifully simple, lightweight component.
And now for the real aha moment, packaging this Java app into an optimized Docker container. Take a look at how the Docker file explicitly copies the Gradle build files first,
downloading the dependencies before it even touches the source code. This specific layering trick is huge. It stops Docker from re-downloading all those heavy Java dependencies every single time you tweak just one line of application code. I'm telling you, it saves massive amounts of build time.
Okay, Section 5. Executing containerized tests.
All right, so our application is perfectly containerized. Now let's actually execute some automated tests against it. Here we see that theoretical Arrange-Act-Assert syntax applied in real life inside our Java unit test file. It's a super simple calculator addition test just to ground the theory. We arrange by creating a new calculator object. We act by passing the numbers 2 and 3 into the add method. And finally, we assert that the expected result is indeed 5.
But here's the best part. Rather than running this locally, we can run these tests directly inside the container. We just override the Dockerfile's CMD instruction at runtime with Gradle test. If you look at the terminal output, you can see Tomcat initializing and the Spring Boot tests executing perfectly in complete isolation. You can literally drop this exact process straight into your CI/CD shell script.
Let's push it one step further, though, all the way to our acceptance tests. Best practice says we should keep our test code strictly separate from our application code. So here's what we do. We spin up our Java application container on port 8080. Then we spin up a totally separate container, but this time it's running .NET and C# test scripts. By using the Docker network host flag, our C# container uses an HTTP client to hit the Java API endpoints exactly like a real user would. This proves our application works perfectly as a total black box.
Which brings us to our final section, Section 6, Best Practices and Debugging.
To wrap things up today, let's go over some crucial production-ready advice for managing these environments. First off, always isolate your testing network from production using separate virtual networks or namespaces. Second, manage your test data carefully so your tests are actually repeatable. But here is the real pro tip. Apply resource constraints. By putting hard CPU and memory limits on your Docker containers, you prevent this incredibly annoying situation where tests randomly fail just because the host machine was under a heavy load. And finally, utilize orchestration tools like Kubernetes or Docker Swarm if you're scaling up to a massive number of containers.
Okay, but what about when a test mysteriously fails? Because, let's be real, it will happen. Well, always start by checking your Docker container logs. But if the logs don't give you the golden answer, don't just guess, equip yourself with the right tools. You can drop directly into a running container shell by using the docker container exec command. That lets you inspect the file system and environment variables firsthand. Or even better, you can hook your IDE debugger, like VS Code, straight into the containerized environment to step through the code as it actually runs.
And that brings us to the end of our explainer. But I want to leave you with a bit of a provocative question to chew on. Is your current testing environment truly mimicking production? Or are you still falling back on the old, "it works on my machine" excuse? I challenge you to audit your CI/CD pipelines this week. Take a look and see where you can implement isolated Docker testing today to kill those bottlenecks for good. Thanks so much for joining me, and keep building great things.